Good morning. We will continue today constructing some classes of generalized diffusion processes. I would like to recall that we have the following situation. Let Bsx a function Bsx defined on this set with its values being symmetric non-negative definite operators be given, like this function be given, okay? And suppose that G S X T Y is the fundamental solution to the corresponding parabolic equation. So we suppose that Bsx is such that there exists such a fundamental solution. Okay, and if additionally vector valued function Asx Sx from 0t cross RB be given. So we denote by G S X T Y the fundamental solution to the parabolic equation of this type U prime S plus A S X U prime plus 1/2 trace B S X U second prime equals 0. Okay, and this one is the fundamental solution to this equation 1/2 trace B S X U second prime X X equals 0. Okay. We saw that these two functions, G and G capital, are connected by a pair of equations. One of them is integral differential one, and the second one is integral equation. Those equations are held if Asx and Bsx satisfy the conditions of the theorem under which these solutions G capital and G exist. Okay, and after that we managed to prove that if P norm of a given function Asx, that is defined as integral from 0 to t d tau integral a tau z no, is finite. We can solve each one of those equations if Bsx is the same as before and norm A and this vector field is such that for some p greater than d plus 2, for some p greater than d plus 2 is finite. Okay, and we proved that now G capital is a solution to each one of those equations, and it can be considered as a generalized solution to this equation because we cannot guarantee that the second derivative of this function with respect to x exists. Okay? So we can ask ourselves, in what sense this process with such A and B, in what sense that process is a diffusion one? So I would like to write down the following relations that this function G capital satisfies. We saw that integral y minus x theta g s x tau z dz is equal to integral the tau integral over rd a tau z theta g s x tau z dz for each theta from rd. This is the first relation, and the second one is as follows: y minus x theta squared g s x tau z dz is equal integral rd b tau z theta g s x tau z dz plus two integrals, the tau integral over rd y z minus x theta a tau z theta g s x tau z dz. Okay? And I would like to recall that the solution to this function for such a and b, now we have this condition on this function for some p, some p greater than d plus 2. Okay, and these two relations are fulfilled, and we have the following estimation: gsx tau z is less than or equal to some constant tau minus s to the power minus d over 2 exp minus mu z minus x squared over tau minus s. Mu and k are some positive constants. Okay? And now let us try to verify whether the conditions in the definition of diffusion in the sense of Kolmogorov, whether they are fulfilled or not. It is clear that the first we can verify the sufficient condition if I consider this integral dz from this inequality. It follows that this is all small of t minus s square, of t minus s square. It is very easy to establish that. Okay, so right,
tau minus s.
yes, thank you, tau. I'm sorry. Okay, now it is not difficult to verify that this integral divided by t minus s goes to 0. I would like to explain why. Let us denote this integral by this symbol. So, absolute value of this integral is less than theta square, and I write down here norm A P. Okay, and I must multiply it by integral the tau integral over RD z minus x norm of this vector to the power p p over p minus 1. Okay, and this, so let us write down here constant. Okay, so here we have tau minus s to the power minus d over 2 p over p minus 1. Okay, and the integral of okay, and exponent minus mu p over p minus 1 z minus x square over tau minus s dz, and we have to write here to the power p minus 1 over p. So let us calculate this integral. Gives some constant, so we have some new constant k tilde theta square norm a p, and this integral from s to t tau minus s to the power minus d over 2 p minus 1 from this plus p over 2 p minus 1. Okay, I make in this integral substitution z minus x over square root tau minus s equals y. So I have to write down here one more item. D over 2. Okay. Yes? This one and this exponent gives it and some constant, d tau. And let us calculate what is it. Minus d over 2 p minus 1, so minus d over 2 p minus 1. This is the first one. Okay, okay, plus p over 2 pi minus p minus 1 and plus d over 2. So we have here the following: p minus d over 2 p minus 1. Okay, tau minus s to the power, to this power. Okay, so after integration we will obtain p minus d plus p minus d over 2 p minus 1 plus 1. So t minus s, t minus s will be, after integrating, in this power. Okay? And I forgot to write down here this exponent, yes, p minus 1 over p. So we have to multiply it by p minus 1 over p. We have p minus s to the power p minus d over 2p plus p minus 1 over p. Okay, we know that this is greater than 2. So this number is strictly greater than 1 over p. This number, this exponent is greater than 1 over p plus 1 minus 1 over p. So this number is strictly less than 1. This number is strictly greater than 1. Okay? And it means that if I divide it by t minus s, this integral goes to 0. Okay. Okay. And what about this integral? This integral, let us denote it by this symbol. 2 is equal to t minus s b s x theta theta plus integral tau integral over rd, the difference between b tau z minus b sx theta theta g sx tau z dz. Okay, but this function satisfies the Hilbert condition, so it is easy to check that this goes to 0. So we have just proved that if I divide this by t minus s, it converges to bsx theta theta. If I'm sorry, here must be t. sorry. You see tau, this, it must be t in those relations. I'm sorry. So if t goes to s, this integral goes to this quadratic form. Okay. So you see the first condition in the Kolmogorov's definition of a diffusion is fulfilled, the first and the third. And what about drift? You see, if I divide this integral by t minus s, if a tau z is continuous, so we can expect that this integral goes to this linear form asx theta. But we have not continuous function. It is integrable to the power, to some power p greater than d plus 2. Okay, so we cannot guarantee that this integral divided by t minus s goes to asx theta. But it is a very easy exercise to prove the following relation. Suppose that c s x s x from 0 to t cross RD is a continuous compactly supported function. Compactly supported function. Okay, let us multiply consider the following integral. Integral psi s x 1 over delta integral y minus x theta g s x s plus delta y dy. Okay, and the s dx. So this is the expression that is taken from the definition, Kolmogorov's definition of a diffusion, the first limit. Okay, and I cannot guarantee that as delta goes to 0, this goes to a sx. But if I integrate, so this converges. This converges to the integral as delta goes to 0, to the integral from 0 to t, integral over rd, psi s x, a s x, ds dx. So this is not, so we have constructed not Kolmodorov's diffusion, but
not ASX times theta? Where
excuse me?
where did the theta go?
Oh, theta. Yes.
Times
Thank you.
theta.
Thank you. Theta. Thank you. So this process is not a diffusion in Kolmogorov sense, but something close, okay? In some weaker sense, this limit coincides with this form. Okay. Now I would like to say a few words about homogeneous processes. So now we suppose that our functions b and a do not depend on time. They are functions only of the variable x. And suppose that b of x is uniformly non-degenerated, positive definite and bounded function, and it satisfies the Helder, it is Helder continuous with some constants k, maybe in n and alpha. Okay, and the function a of x, if it is bounded and Helder continuous with the same constants, so there exists a fundamental solution of how to write down the parabolic equation in this case. And what is the fundamental solution? I would like to explain. As far as I remember, I have already talked about the homogeneous processes, and we if we have a Markov process x of t m s t p s x, you see that such a process corresponds to some solution to the Kolmogorov-Takman equation. PSX T gamma and if it turns out that this transition probability is such that PSX S plus T gamma does not depend on S, so we call such a process homogeneous. This is a homogeneous in time Markov process. Okay, in this case there exists, this is a function of t, x and gamma, okay? And I would like to use the same notation, and this is a new transition probability, and the old this one can be written through nu in the following way: pt minus s x hammer. This is nu. This is so the you see the Kolmogorov backward equation was written as follows: plus ASX U second prime of U prime X plus 1/2 trace PSX U second prime equals 0. Okay?
A is a function on x only, not on s. You just recall.
Yes, this is in general case. This equation for such a process, okay? Diffusion, if it is diffusion and something else fulfilled, then the function u s x t phi being equal to integral phi of y p s x t dy satisfies this equation for sx 0t rd. Okay, and now if a of x and b of x are the functions that do not depend on s, so we have this situation. The fundamental solution will be, in fact, a function of 3 arguments, t, x, and y, and this function in this term will be written as follows: ut minus s x phi of y p t minus s x dy. So u prime s is, in this situation, is minus u over t, okay? And so the equation will be as follows. d u prime t minus a of x u prime x minus 1/2 trace b of x u second prime x equals 0. Okay? And now the final condition was ut minus x t phi is equal to phi of x. Okay? Now, if s goes to t minus s goes to 0, so this is the initial condition: 0 x phi equals phi of x. This is a new function, and I consider it, this is an old function, so for new function we have the following: Cauchy problem. This is the consequence of the theorem by Kolmogorov about this function. It satisfies the Kolmogorov backward equation as a function of s. And this function satisfies this Kolmogorov backward equation in homogeneous case. Okay? So now I would like to say that there is no reason in fixing s if you have a continuous, homogeneous process. There is no sense in fixing. We can consider the family of measure P0x in this sense, because you see, if I consider this probability, and I know that my process is homogeneous, then I can write down that this is integral from RD, integral over gamma P S X T gamma. Or maybe without integral. Okay? So, but it is the same that P T minus S X, maybe P0 X T minus S gamma Okay, if I add s here and here, I have the same, but this addition does not change the value of this function. Okay, so we will use the following notation for homogeneous processes. Px mt is m0t. 0, we do not write 0. Okay, so if you look throughout our construction, a fundamental solution to now to this equation, you will see that those fundamental solutions are some functions of 3 arguments. So g t x y is a fundamental solution to that equation, with a being equal to 0. Okay? And g capital t x y fundamental solution. So this is fundamental solution. A equals 0 and b is a function. And here fundamental solution a and b. Okay? So if a and b are Hilbert continuous, and this is uniformly non-degenerated, bounded, then we have the following 2 equations that connected these 2 fundamental solutions. G t x y equals g t x y plus integral d tau integral g s x g tau x z a of z nabla z g capital t minus tau z y dz. This is the first one, and this is integral differential equation, and the following one, g t x y equals g t x y plus integral d tau integral, this is x or d, g capital tau x z a of z nabla z g t minus tau z y dz. So we have these 2 equations, that 2 relations between these fundamental solution. This corresponds to the full equation with a and b, and this a equals 0, and the same b. Okay, let us make a little break. Let us continue our considerations. So, we have this pair of equations, and now we can suppose that a of x is not a smooth function, but somewhat more general. It turns out that these equations can be solved under the following assumption about the function a. Norm a, p. This time, this is one integral. Is finite. It turns out that if we suppose that this norm is finite for some p greater than d, p greater than, then we can apply the method of successive approximations to each one of these equations and obtain the function g and the following estimation on that function are true g t x y is less than constant t to the power minus d over 2 x minus mu y minus x square over t. With some positive constants k and mu, and the derivative will be estimated the same expression, but here d plus 1 over 2. Okay? Okay. And the following relations are fulfilled, similar to those that we have in the non-homogeneous case. Integral over rd y minus x theta. G T x y dy equals integral the tau integral a tau y theta g tau x y dy. This is the first one, and the second integral y minus x theta square g t x y dy equals integral the tau integral b of y theta theta g tau x y dy plus two integrals the tau integral y minus x theta a of y theta g tau x y dy. And you see here we have the same situation. The process that corresponds to this transition probability density is not a diffusion in Kolmogorov sense, but the first condition and the third one are fulfilled in this situation. And only the problem is with this integral. It is being divided by t. It can, how to say, we cannot guarantee that this divided by t, this goes to a of x theta as t goes to 0.
And we have a should only depend on y.
Oh yes, yes. Thank you. Thank you. But it is an easy exercise to show that for a function psi of x that is continuous and compactly supported, we have the following relation. Integral over Rd psi of x 1 over t integral over Rd y minus x theta g tau gt x y dy dx converges as t goes to 0 converges to the integral over r deep c of x a of x dx. So in sum, you see the Kolmogorov's condition does not fulfill
A
a
times
theta.
theta.
Thank you. A of x. A of x theta dx. So this process is not a diffusion in Kolmogorov sense, but in some generalized sense. The drift is this function a of x. And we can ask ourselves, and what a phenomena in the nature are described by such a process. Its diffusion operator is a nice one function, uniformly non-degenerated, Hölder continuous, bounded, okay? But its drift vector is a locally unbounded function. So I propose the following interpretation to such a process. There must be vertices in a liquid. If we consider this process as that is intended to describe the motion of a little particle in a liquid. But liquid may have some vertices, and at some points of the space, the velocity is very high. So it is natural to consider such a model for such a diffusion for which this macroscopic velocity, this is macroscopic velocity at the point x. This macroscopic velocity is very large. Okay, and now the last fact about these processes I would like to formulate. You see, this estimation shows that that the corresponding process can be chosen such that its trajectories are continuous functions. Okay? So the continuity condition for the corresponding process is fulfilled here. So we can construct on the space of all continuous functions C 0 T RB, we can construct on the sigma algebra M T, I can construct the measure Px, okay, that this measure is generated by this transition probability density. I would like to denote it by AB. So this is the measure that on the space of continuous function that starts from the point x at the instant, at the initial instant of time, and that measure is generated by this transition probability density. And we can consider the measure on the same space that corresponds zero drift vector and the same diffusion operator. Okay? And what about how these measures are connected one with the other one? The theorem can be formulated as follows. If D is less than or equal to 2 and P equals dP, so we have this vector field such that this norm is finite for some P, for some P greater than G. Okay? So if D is not less than 2 and P is greater, or D equals 1 and P greater than 2, then Px we can consider these measures on the space because our coefficients do not depend on t, so this transition probability density is defined for every t. positive. Okay. So I assert that the restriction of this measure on the sigma algebra and T for any T is equivalent to the restriction of measure P0b, PAB is equivalent to the corresponding restriction of measure P0b on the sigma algebra MT for any T. And you see, there is some gap. Yeah. No, ладно. So if D equals 1 and P is greater than 1, but integral is equal to infinity for some n, then these measures are not equivalent to measures to the corresponding restriction of measure P0b on the sigma algebra MT for any T.
How it is possible? So A belongs to LP
Yes.
and P is greater than 1. So
P is greater than 1, but if it is greater than 2, greater or equal.
no, I mean assume that if A belongs to LP, then this integral is finite.
Square. Thank you. Square. Thank you. We can write down not absolute value, but a of x square. So if P is such that this function exists, because P greater than D in this case, I can construct this function. But if it turns out that this function is not integrable, square integrable, so these measures are not equivalent. It is very easy to explain why is it so? Because if b of x equals 1 in one-dimensional case, okay? So P0b, this is the Wiener measure, okay? And this is a Wiener measure, a process, a Wiener process plus some drift coefficient, okay? And if that drift is not integrable square integrable, there exists some interval where we have that this is equal. So such a process cannot be equivalent to Wiener measure, because the necessary and sufficient condition for the equivalent, for these measures to be equivalent in this case is exactly square norm of A must be finite. You see here. With respect to any
Recording
measure,
in progress.
with respect to any measure, Wiener and this one. But we know that if such an integral is infinite, so expectation, so integral, not expectation, so the integral from 0 to t, a of w s ds is not well defined in this case. A square. Okay, is not in this case. In this case, it is not well defined, and we have some condition.
So we can prove this if we know local times, something like this.
No, this there is a very simple.
Or we have to know Girshanov theorem.
Yes, but the fact that if this integral is infinite, then this integral is not defined is for Wiener process. For Wiener process, is in the book by Skorhod and Slobodanuk, limit theorems for random walks. Is a very simple proof. If this is in order to define this integral, the following condition is necessary and sufficient. Such integrals must be finite for any n, for any finite n. Then this integral is this is a very simple. So you see that in a general case, these measures are equivalent. Okay? So, in some sense, what does it mean? It means that some properties of a diffusion without drift are close to the properties of a process with drift, even in this case where AP is finite for some P greater than D. But there is some exception, okay? Okay, so this is the finish of consideration of the processes with integrable with integrable drift. You can find out some details of all our considerations in my book that is called Generalized Diffusion Processes. It was published here in Kiev in 1982 in Russian language, and it was translated by American Mathematical Society into English in 1990. Now we will consider the following processes that are called skew, Brownian motion, we will consider one-dimensional things. So d equals 1, and I would like to write down r instead of r1. And let a starting process will be Wiener process or Brownian motion. So g t x y equals 2 pi t to the power minus 1/2 x minus y minus x squared over 2t, where t is positive, x from R and y from R. And now I am going to show that such a process can be perturbed by the following drift coefficient. A of x equals some real constant and times Dirac's function. Dirac's function that is a generalized function such that it acts on a test function in the following way, according to the following rule. This is phi, the value of our test function at the point 0, x being equal to 0. So I somewhat later I will write down those two equations for the function g. Okay, but now I would like to, you see, we have that Wiener process is connected, is related to the following Cauchy problem: minus 1/2 u second prime equals 0. This is equality for the homogeneous function. This is analogy to Kolmogorov's backward equation. And now I would like to consider such a process for which this equation should be written as follows: minus q delta of x u prime let us look at this equation attentively and ask ourselves. Here we have delta function. It should be compensated in this equation by what? It is clear that the second derivative must give us delta function. But this means that the first derivative must be discontinuous at the point 0. And we have here a problem. Delta of x should be applied to a discontinuous function, to a function that have a jump at 0. How to generalize this rule? This rule on that situation when phi is not continuous at the point 0. I propose the following rule: delta phi equals 1/2 phi 0 plus phi 0 minus. It is some generalization of this rule, okay? If phi is continuous, we have this rule. So we will use this relation for a generalization of Dirac delta function. Okay? But as I understand, my time is over, so thank you. See you next Tuesday.